In today's lecture, we will explore the world of support vector machines, a powerful tool in machine learning. SVMs are known for their ability to make precise classifications, making them essential in various applications. In this line of code, over here, we will see how random data is generated for classification. This line of code over here sets the random seed for the NumPy random number generator to 10. Setting a seed ensures that you get the same random numbers every time you run the code, which is useful for reproducibility. Later on, in this line of code, we are generating random data in the form of 2D NumPy array X. The npy.random.randn, this function generates random numbers from a standard normal distribution, mean 0 and standard deviation 1. It creates an array with 30 rows, as you can see over here, 30, and 2 columns, effectively generating 30 data points with 2 features each. In our next line of code, this line generates target labels y for the data points. It uses np.repeat method to create an array by repeating the values, example 1, comma 0, 15 times each. As a result, Y contains 30 elements, with the first 15 elements being 1 and next 15 elements being 0. This is a binary classification problem where the goal might be to classify data points into two classes labeled as 1 and 0. We will display our first three rows and columns now in this line of code using NumPy array slicing. As you can see over here, our start and end is 3. So it will start from 0 and end till 3. So that's how it will print the array numbers. So over here, we have just printed our first three rows of the X array and first three elements of Y array. So our slicing works from 0 till one element before the end. So that's why 0, 1 and 2 has been printed over here. In our next lines of code, we have already seen scatter function. So what it's doing is it's plotting the data points from X array on a 2D plane where this both values represents first feature and second feature for all data points. This argument over here specifies the colors of the points based on the values in the Y array. And again, these two lines of code sets labels for x-axis and y-axis of the plot respectively. In this case, x1 and x2 are used as labels to indicate which features are being plotted on each axis. This is how we have got a scatter plot where data points are displayed in different colors based on their corresponding labels, and axes are labeled as x1 and x2. This can help us visualize the distribution of our data and see if there is any separation between two classes based on features x1 and x2. Moving on to our next lines of code. Here we are going to train a support vector machine classifier. Let's see how we will do it. In this line of code, we are creating an instance of support vector machine classifier using SVC class, as we can see over here, from scikit-learn library. C is equal to 3. This parameter controls the trade-off between maximizing the margin, large C, and minimizing the classification error, small c, in the SVM. A larger C allows for a smaller margin but fewer misclassified points. And in our second argument, the kernel is equal to linear. This parameter specifies that we are using a linear kernel, which means the decision boundary will be a straight line in the feature space. The next line of code, this line uses a fit function which fits which is trains the SVM classifier M on the input data X, X and corresponding labels Y. The SVM will learn to find the optimal decision boundary that separates two classes 1 and 0 based on the features in X. And later on, plot underscore SVC. This function calls the plot SVC function that we have defined earlier to visualize the decision boundaries and support vectors of trained SVM classifier. So in this output, we can see that plot SVC function have plotted the decision boundaries, support vectors and data points on 2D plane, allowing us to visualize how well the SVM has learned to separate two classes, as you can see here in the separation line. So this is how we are seeing SVM's decision boundaries and support vectors in the resulting plot. Uh, and this is helping us to assess performance of the classifier on our data. Let's move on to our next line of code. Over here, m.coefficient, this attribute of scikit-learn SVM classifier returns the coefficients of the linear decision boundary. However, it's important to note that this attribute is only available when you use a linear kernel, because linear SVMs create linear decision boundaries. And as we can see, we have chosen a linear kernel over here. That is why we are able to use this argument. In the output, we can see that this line of code returns array of shape, where each row of array corresponds to a class and each column corresponds to a feature. The values in this array represents the coefficients of the linear equation defining the decision boundary. In this line of code, we are trying to find the indices of the support vector. So m.support attribute of the scikit-learn returns an array that contains the indices of support vectors. Support vectors are the data points from the training set that lie closest to the decision boundary and play a crucial role in defining the decision boundary of the SVM. Let's have a look at our next code snippet. These lines of code we have seen earlier as well. So this line over here is just another SVM classifier with a linear kernel, but sets a smaller regularization parameter C to 0.3. As in our earlier example, we have seen C equals to 3, which was a narrower margin and fewer support vectors. Like it showed us narrower margin and fewer support vectors, while the second SVM right over here, this is using C equals to 0.3, and this may have a wider margin and potentially more support vectors. This line over here again trains the second SVM on the same input data X and Y, and again over here this function is used to visualize the decision boundaries and support vectors of the second trained SVM classifier. Thus, by visualizing these SVMs, we can absorb uh, and observe how changing the regularization parameter affects the model's behavior in terms of decision boundaries and support vector placement. This can provide insights into trade-offs between model complexity and generalization in SVM.